we're looking at lesson 2.07 called Radical Ideas. And today's objective is I can use the rules of exponents and rules of radicals to rewrite an exponential function in 2 out of 2 problems. So we've talked about some rules of exponents already. We haven't talked about rules of radicals yet. In fact, we haven't even discussed what radicals are. So let's talk about that first. So a radical is just another name for a root. So you can see here we have 6 root 14 or 3 root a, 9 root 512. All of these are examples of radicals. And the symbol itself, this little table that sits over a number, that is called a radical sign. So when we talk about radicals, we're just talking about roots. Rooting a number. So what kind of exponents produce radicals? Can you remember, can you think back to our exponent rules? We raised a number to a particular exponent and it would produce a radical. It would produce a root. What kind of exponent was that? Was it an integer? Was it a negative number? Was it a fraction? It was actually a fraction. If you'll recall, we took the denominator of an exponent and we put it into a root. In this case, it would be a root 2, because 2 is on the denominator. So here's a reminder of the rules we used to turn fraction exponents, or what we also called rational exponents. That just means a fraction. We turned fraction exponents into radical signs. Once again, we took the denominator and we made it into a root. Take the denominator, turn it into a root. In this case, we also had a numerator, and we just leave the numerator where it is. We just let it still be an exponent. We just took the denominator and made it into a root. So let's use these rules to rewrite some exponent fractions as radicals. Now, this isn't necessarily simplifying, it's just putting it in another form. And you may find that as you work with exponents or you work with radicals, that looking at a problem one way makes more sense than the other way. So it can help us to have the skill to be able to switch between the two. So we're going to write 7 to the 3/5 in radical form. We'll use this rule up here. Our denominator will become our root. Our numerator will stay an exponent. All right, so here we go. We're going to make a root. 7 stays underneath. Our denominator is going to be what our root is, the base of our root, 5 root 7. And then we're going to leave the numerator where it is as an exponent. That's how we write that as a radical. Okay, how about 36 to the 1/2? How do we write that one? Well, we're going to take our 2 denominator and write it as a radical. Now, if I didn't put a 2 there, we understand that implicitly, if they've left it blank, that's a 2. So this will be square root of 36. But wait a second, can't we simplify square root of 36? Isn't 36 a perfect square? It is, so this simplifies down to 6. So that's maybe one case where it makes sense to write it as a radical. We didn't necessarily see that this was a perfect square that could be reduced or could be simplified until we wrote it in this form, in this radical form. And then it registered in our brain that this is a perfect square, and we can simplify it. So let's look at a couple more examples. Write these expressions as radicals. Okay. So we have a couple of options here. We could have simplified these exponents first, right? When we multiply, we have a rule that says we can add the exponents. So that's one option to simplify this, but it says to write it as a radical. So let's try writing them as a radical and see what happens. So I'm going to use that rule up there. My denominator becomes the base, and I have a to the 4th exponent. Same thing over here, my denominator becomes the base, and now I have a 2 exponent. But this is actually, if you look at this bit right here, we can say 3 root 12 is just x. We can put in a variable for it if we want to. And then we're just looking at x to the 4th times x squared, right? This is x and this is x again. We know how to simplify that. That's just x to the 6th. 4 plus 2 is 6. So what this really becomes is cube root 12 to the 6th. Now we can write this back in exponent form, and we see this is 6 over 3, which is just 12 squared. Well, 12 squared is actually really easy to write as a number. That's just 144. So this simplified all the way down to a basic number. Now, if we just used the original exponent rules, we could have actually added those together and gotten 12 to the 4/3 plus 2/3, which is 12 to the 6/3, which equals 12 squared. So we got the same answer. 144 is 12 squared. We just took a few different routes to get there. Maybe one makes more sense to your brain. This one certainly seemed less complicated this time. The radical way seemed more complicated. Neither of them is wrong. Both of them are totally viable options to take. We're just figuring out our own preferences and how we can manipulate these back and forth. So let's look at our next one. X to the 9th times y squared to the 1/3. How might we write this as radical? Well, we can take this 1/3 and turn it into a root 3, or rather a 3 root, x to the 9th y squared. But we also know that we can divide out this x to the 9th like this. X to the 9th is just x to the 3rd times x to the 3rd times x to the 3rd, right? Because 3 plus 3 plus 3 is 9. And our y squared stays where it is. So we just divided out, we basically factored out x to the 3rds. Well, now I can write these separately. Cube root x to the 3rd, cube root x to the 3rd, cube root x to the 3rd, and then cube root y squared. See how we just took each of these individually? We can do that with radicals. And now that cube root will cancel, that cube root will cancel, and that cube root will cancel. These ones don't cancel because that's a 3 and a 2, but the rest of these did, and we get x times x times x times cube root y squared. Now x times x times x is just x cubed times cube root y squared. There is our simplified version in radical form. Now remember, we had a few other options here. We could have used our distribution over multiplication if we wanted to, and just multiplied that in which case we would have gotten x to the 9 over 3 times y to the 2 over 3. 9 over 3 reduces to 3, and we get x cubed times y to the 2 over 3. Once again, y to the 2 over 3 is the same thing as that. So we, once again, got the same answer. Now we can also go the other direction. We can go from a radical to an exponent. So how would we write these expressions as exponents instead of radicals? Well, our root is going to go in the denominator of the exponent, and the existing exponent is going to become the numerator. So we have the fraction, 5 is the denominator, and 2 is the numerator. So on this next one, We have a root. It doesn't have a number here. We remember that means there's an implicit 2. So that's the number that's going to go in the denominator of our exponents. So let's take this first expression right here, 2 to the 5th square rooted. Okay, so we're going to keep the exponent in the numerator, put the root in the denominator. Then we'll do the same thing with the 3 expression. 3 stays our base, 4 goes to the numerator, and we get a 2 in the denominator. Now 5 halves can't be simplified. That's simplified as far as I'll go, but 4 over 2, that's just 2, so we can actually simplify that a little bit more. 2 to the 5 halves times 3 squared. So that's how we'd write that with exponents. How about this one? X to the 8th, y to the 21st, and we're going to cube root that. 3 root. Well, let's use this rule up here. We get x to the 8 over 3, y to the 21 over 3. This is our denominator for both of those exponents. These are the numerators. 21 over 3 can reduce, so we get x to the 8 over 3 times y to the 21 divided by 3 is 7. So there's our answer as an exponent. Or as two exponents actually. So we have some radical rules too. We've talked about a bunch of exponent rules. Here's some radical rules. We've been using these already in the assignments, so these should look pretty familiar. If we raise to an exponent and then we root it, those will cancel. So you can cancel those and it just becomes a. You can also distribute a radical over multiplication. So n root of ab is the same thing as n root a times n root b. And you can distribute a radical over division. N root a over b is the same thing as n root a over n root b. We're going to skip this slide and just come straight to this one. So we can get that all on the same screen. There we go. So these are our rules of exponents and radicals, all on one screen. These are all the ones we're going to go over. So if you have these in your notes already, we've got some new ones with the radical rules over here. Those are the new ones for today. This is a really great slide for your notes. I'm going to post this one separately in the content as well, so you can just get this picture for your notes. These are all the exponent rules and all the radical rules you'll need to switch between the two. It's a very busy slide. There's a lot going on here. But we learned these all individually, right? So you can just use this as a reference. So you see a problem and you're like, looks like we're dividing. Where can I find some division rules? I can go through these and be like, oh, same base division right there. There's division. And there's the rule I need. Or maybe it's a distribution over division. So it'll be over there. So the main purpose of today is we are just going to practice these. This is sort of similar to when we learn our multiplication tables or addition and subtraction. This is just another tool in our toolbox, and we sort of need to practice it several times to get used to how to do it. We don't have any applications in this lesson. Well, we're doing applications outside of it. This is just a skill that we need to be able to manipulate algebraic expressions that have exponents in them. So we're just going to go through several problems. Simplify the expressions by factoring and using rules of radicals and or exponents. So we're kind of free to do whatever we want here with the exponent rules, with the radical rules. We can use the ones that make sense to us and possibly get it in a simpler form. And if not, we can at least manipulate it into a different form and see if that looks better to us or makes more sense. So what might we do to simplify this one? We can use our rules over distribution our rules over division rather. And this is going to be 9 minus 6. When we divide with the same base, that means we're going to subtract the exponents. So this just simplifies to 7 to the third. How about this next one? We have 3 to the 5th times 4 squared divided by 3 to the 8th. Now when we use our division rules and our multiplication rules, we need the same base. Well, notice 3 here and 3 here have the same base, but 4 is a different base. So we can't combine that 4 with the others. The only ones we can combine are these two. So we can use that division rule again, 3 to the 5 minus 8. And then we just have to bring the 4 squared along. There's nothing we can really do with it. 5 minus 8 is negative 3 times 4 squared. And we could leave it there if we wanted to, but we also know something about negative exponents. The rule about negative exponents is we put it in the bottom of a fraction with a positive exponent. So this is the same thing as 4 squared over 3 cubed. So that's a little bit simpler than our original fraction. We might prefer to work with this instead. Or maybe for what we're using it for, this might be easier to use as well. It's up to you. Let's look at a couple more examples. Simplify the expressions by factoring and using rules of radicals and their exponents. Okay, x to the 8th, 3 rooted. How might we do that? Well, one way we can think of this is how we've been factoring in the assignments. We can expand this as x times x times x 8 times. So there's 4, 5, 6, 7, 8. Whew. And because we're doing a 3 root, we're looking for sets of 3. So there's 3, there's 3, and we have 2 left over. So we can write x to the 8th as x to the 3rd, this set of 3, times x to the 3rd, this set of 3. And then we have 2 left over, so x squared. So 3 plus 3 plus 2 is 8, so x to the 8th. And all of that is under a cube root. And now we know we can separate these out. So this is cube root x cubed times cube root x cubed times x squared. Oh, cube root x squared, there we go. We distributed the root or the radical over each expression. This cube root will cancel, this cube root will cancel, and we get x times cube root x squared. X times x is x squared. So finally we get x squared cube root x squared. So now that may be not as simple to write as this, but maybe it's more useful for what you're using for. You never know. Just knowing that we have the option to change it between those two forms might be helpful. How about root 27? How might we simplify that one? We can factor this again. 3 times 9 is 27, and then 9 factors into 3 and 3. This is a square root, so we're looking for pairs, groups of 2. We can write this as the square root of 3 squared times 3, which splits out to square root of 3 squared times square root of 3. Square and square root will cancel, and we just get 3 root 3. So that is the same as the square root of 27, 3 root 3. We just factored out a 9. We factored out a 9 and then square rooted it. You may find root 27 handier to use in your equation that it shows up in, but 3 root 3 might be handier. Just switching between them might be helpful. at some more examples. Square root of 25a to the 6th. How might we handle that? Maybe we can split these out. Root 25 times root a to the 6th, right? We can just distribute the radical over multiplication. Now we know that root 25 is 5. That's a perfect square. And then we can use our rational exponent rule here and get a to the 6 over 2. The exponent stays, the 2 becomes the denominator. 6 over 2 is just 3. That simplifies to 3, so we get 5a cubed. That's much simpler than this one. So sometimes switching to another form can help us simplify. How about this next one? We have a couple of different ways we can approach this. We have a few different steps. What should we do first? Maybe let's apply this division rule. We can do x to the 6 minus 2, all raised to the 1/2. This is going to be 6 minus 2 is 4, x to the 4th raised to the 1/2. And then we know an exponent raised to another exponent, we're going to multiply those. This is x to the 4 times 1/2. This becomes x squared. So x squared is way simpler than this mess up here. It definitely helped us to simplify using exponent rules there. More examples. Maybe let's skip this one. Let's do this one. So how might you approach this one? Pause the video, see if you can do this first one on your own, and then see if you get the same answer. So we can multiply the 2 and the 7. A power raised to another power is going to be multiplying the exponents. So we get 3 to the 2 times 7, and then we'll just bring this expression along, times 3 to the negative 10. 2 times 7 is 14, so this is 3 to the 14th times 3 to the negative 10. When we multiply with the same base, that means we can add the exponents. So we get 3 to the 14th plus negative 10. 14 plus negative 10 is going to be positive 4. So overall, this simplifies to 3 to the 4th. Much simpler than this mess up here. And how about 1 over 2 to the negative 4th? This is tricky because negative exponents we already expect to show up as a fraction, right? But now we've put it in a fraction. If this were 1 over 2 to the 4th, then we could just say this is 2 to the negative 4th. That was our negative exponent rule. But now we've got a negative in this denominator. We have to deal with that. Something's different here. So what do we do? Well, one way we can look at this is say 2 to the negative 4th, right? 2 to the negative 4th is going to be 1 over 2 to the 4th. So all of that goes into the denominator. We get 1 over 2 to the 4th. We've got a fraction in a fraction. But we have a rule when we have fractions in fractions that says we can take the denominator and flip it upside down, then multiply. So this is going to be the same thing as 1 times, flip the denominator upside down, 2 to the 4th over 1. 1 times 2 to the 4th is just 2 to the 4th. Divided by 1 is still 2 to the 4th. So overall we get just 2 to the 4th. And now we don't have a negative exponent or a fraction. That's nice. Both of those fell out by simplifying. Another way you could think of this is let's just put a variable in here. Let's call y. Let's say y is 2 to the negative 4th. So this would just be 1 over y, right? 1 over y. Using our negative exponent rule, that's just y to the negative 1. Now we can plug this back in for y. So 2 to the negative 4th to the negative 1. And we know that a power raised to another power multiplies. So this is the same thing as 2 to the negative 4 times negative 1. Negative 4 times negative 1 is going to be a positive 4. So again, we arrived at the same answer with a different method. Whichever way makes more sense to your brain is totally valid. So in today's objective, we are using the rules of exponents and the rules of radicals to rewrite an exponential function in 2 out of 2 problems. So we're just doing practice, going back and forth between exponents and radicals.